Welcome students. In this video, we will learn about the decimal expansion of real numbers. We know that every real number is either rational or irrational. Rational numbers can be written in the form p by q, but irrational numbers cannot be expressed in this form. Ever wondered what makes 1 by 3 different from 1 by 4? They are both rational numbers, but when you press the division button, their decimal expansions tell a completely different story. In this video, we will view rational and irrational numbers in a new way, using their decimal expansions to understand what makes them different. Rational numbers are the well-behaved numbers. Their decimal expansions are always one of two types. Terminating decimals are the simplest. Think of 1 by 8. Divide 1 by 8 and you get 0.125. The division stops or terminates after a finite number of digits. Other examples include 1 by 25 and 1 by 10. To check whether the decimal will terminate or not, the rule is simple. If the denominator is made up of prime factors 2, 5, or both, the decimal will terminate. 8 has only 2 as a prime factor, 25 has only 5, and 10 has both 2 and 5. Therefore, their decimal expansions terminate after a finite number of digits. Now, what about numbers where the division never stops? For example, divide 1 by 3 and you get 0.333. The division never stops. Such numbers are called non-terminating repeating decimals. They go on forever but follow a perfectly repeating pattern. We use a small bar called a vinculum to show the repeating part. To check for non-terminating repeating decimals, factorize the denominator. If the denominator has any prime factor other than 2 or 5, the decimal will repeat. For example, 7 by 9, 1 by 6, and 22 by 7. As you can see, when a decimal has a predictable repeating pattern, it can be written in the form p by q. Use the following steps to convert a non-terminating repeating decimal into a rational number. Let x be the given number. If the number of non-repeating digits after the decimal is m, multiply both sides by 10 to the power m. Now we have repeating block of digits after decimal. If the repeating block contains n digits, multiply both sides of equation 2 by 10 to the power n. The repeating pattern will align. Now subtract equation 2 from equation 3 and solve for x to get the rational number. If you find this process time-consuming, check the short trick to do it in seconds. Now, what do you think about the decimal expansions of irrational numbers? The decimal expansion of an irrational number is the exact opposite of that of a rational number. It does not terminate, it goes on forever. And there is no visible pattern after the decimal point. No block of digits ever repeats. It is not predictable. It appears completely random. Meet the most famous irrational number, pi. Its decimal expansion begins with 3.14159 and continues infinitely without any repeating pattern. Do not confuse pi with 22 by 7. 22 by 7 is a rational number because it has a repeating decimal expansion, but pi is an irrational number. Another example is the square root of any non-perfect square, such as square root of 2. So, if a decimal expansion is non-terminating and non-repeating, the number is irrational. Let's bring it all together. Every real number fit into one of these categories based on its decimal expansion. Next time you see a decimal, you don't even need to know the fraction, just look at its tail. If it goes on forever without repeating, you have found an irrational number. Tell me in the comments, what type of number is this? Is it rational or irrational?